Bernstein inequality is another concentration inequality for bounded random variables. For the sum of bounded random variables. So this is homework. The proof of Bernstein inequality is homework of this course. So the basic idea of the proof is, again, we have to use MGF and Markov inequality. But here we have to use Taylor's expansion to reinterpret the MGF. Okay, so when you reinterpret the MGF using Taylor expansion, in the end you can make a Bernstein inequality. Indeed, there are a lot of materials and proof details in internet, in Google. When you search Bernstein inequality proof, you can see tons of results. I recommend to read all the proof, one of the proof, and understand the proof yourself and rewrite the proof by yourself, okay, without help the pre-written. Okay, so my suggestion is, please don't just copy the existing proof. Understand it, digest it, and write down in your language. Okay. Right. So until now, we have discussed concentration inequalities for independent random variables, for the sum of independent random variables. Azuma Hoeffding's inequality extends the result a little bit to the direction of martingale process. So Azuma Hoeffding's inequality is a concentration measure for martingale process. So what is martingale process? Martingale process is this. So you have the sequence of x, x0, x1, x2, they are sequence of random variable. Here, xi minus xi minus 1 is independent. But the distribution of xi minus xi minus 1 can depend on past history. Previously, all our observations independent to other realization. Okay, even the distribution never affected by any other outcomes. But here in the martingale process, the xi minus xi minus 1, they are independent random coin tossing, even it could be a random coin tossing, but the distribution can be affected by the previous history. Okay, that is the difference, right? And the martingale process is the case expectation of xi minus xi minus 1 for given the previous history is equal to 0, then it satisfies martingale process. Right. So let x0, x1, be a martingale process satisfying xi minus xi minus 1 is bounded by ai and bi for some constant ai and bi. Right, then for all I greater than or equal to 1, okay, if this condition hold, then for all n, for all the time xn, we have this concentration inequality. The probability xn strictly bigger than x0 plus t and xn strictly less than x0 minus t, both concentration probability is upper bounded by exponential minus 2 times t square over summation I1 to n bi minus ai square. This is basically the same with Hoeffding's inequality. In the Hoeffding's inequality, we have this kind of bound, right? I want to n greater than or equal to t is less than or equal to exponential minus 2n t n squared t squared over summation pi minus ai squared. I want to n, right? So basically this is equal to n xi greater than or equal to nt, right? And when we rewrite nt by t prime, this is less than or equal to exponential minus 2 times t prime square summation, right? So basically the same. Azuma Hoeffding's inequality, the property shape exactly the same with the Hoeffding's inequality result. So this is very good, right? Very good news. Even if the sequence of random variable do not follow the independent property, but have some martingale process behavior, still we can apply Hoeffding's inequality result whenever the difference always bounded by some range. Okay, and the outcome is kind of independent. Although the distribution has some dependence to the previous observations. Okay, so the proof of Azuma Hoeffding's inequality also very similar with previous proof techniques. So let x0, x1, be a martingale process with respect to filtration. So here filtration is kind of the past history, the observations up to some point, right? So the fk, the filtration subscript k, indicate all the observation up to time k. So the observation up to random variable xk. Then of course as time goes by, the filtration space becomes expanding. And for all k greater than or equal to 1, the martingale process having this property. So when you take expectation of xk plus 1 for given filtration at time k, this result always equal to xk, right? So the difference between xk plus 1 minus xk, this is always mean zero random variable. But the distribution of xk plus 1 minus xk can depend on the past history. That is martingale process. So when fk is given, x0 to xk also given. So x0 to xk are just constant, and thus the expectation of xk for given fk is just xk. Right. So let's denote by yi the difference between xi minus xi minus 1. Then the expectation of yk for given filtration at point k minus 1 is equal to 0 from the definition of filtration. And from the definition of martingale process, we have this property. Right. And also, since in the theorem statement, we assume that the yi always bounded by AI to the lower side and BI the upper side with probability 1 from the Hoeffding's lemma. For this single random variable yi, we have this. Note that the Hoeffding's lemma does not depend on the distribution shape. For any bounded random variable, we have this inequality. So we can use this and list the difference between xi and xi minus 1 is bounded by ai and bi. Right. So here, to apply Markov inequality and MGF trick, essentially we need to upper bound this expectation of e to the zeta times y1 plus y2 plus up to yk. This is equal to this. When for given filtration at point k plus 1, this is random variable because of yk is not a given value but a random variable. Of course, this depends on the filtration fk minus 1, but still yk is random variable, bounded random variable. So this expectation is expectation with respect to yk, and this outside expectation is expectation with respect to this filtration. Because this filtration also random variable, the sequence from x0 to xk minus 1, it also random vector, random sequence. So this expectation is expectation with respect to this filtration. Right. So here only yk is random variable, so this is just a constant. So we can move this constant to the outside of the inner expectation like this. And from the Hoeffding's lemma, we essentially can bound this. So here there is typo. Sorry, this is this inequality. Right. When you repeat this process again and again, so how to repeat? So this is equal to expectation and expectation e to the zeta y1 plus yk minus 1 for given filtration k minus 2. Then the inner expectation is expectation with respect to this yk minus 1 random variable for given filtration point at point k minus 2, and this expectation is expectation with respect to this filtration. And again, since these terms are constant for given this filtration, so we can move the constant part to the outside of expectation. And then when you apply the Hoeffding's lemma, again you have expectation of exponential of zeta square b k minus 1 minus ak minus 1 square away. In the end, we have this inequality like this, right? And when we have upper bound for this expectation of e to the zeta y1 plus y up to yk, we can easily complete this proof analogously to the proof of Hoeffding's inequality. Only remaining part is optimizing the zeta after applying the Markov inequality. Okay. So using this Azuma Hoeffding's inequality, we can derive McDiarmid inequality as well. And McDiarmid inequality is also very interesting when we have sequence of random variable x1 to xn. They are independent random variable, let's assume. And f be a function satisfying for all I, for all index I, and for all input value x1 to xn and some xi prime. So in other words, there are n input element. So f is kind of out to the n to the scalar valued function with input space n-dimensional real space. And if f is some bounded difference property, like when you deviate one single element, then the value difference is at most ci. That is our assumption on function f. Then with any random variable, if f function satisfies this bounded deviate behavior, from Azuma Hoeffding's inequality, we can show this concentration inequality, the f with random input value x1 through xn minus expectation of this function value deviate by t or minus t is upper bounded by the probability for this event is upper bounded by exponential minus 2t squared over summation I1 to n ci squared. So as you notice, so this inequality shape almost identical to this Azuma Hoeffding's inequality. We just replace bi minus ai by ci, right? And the proof of McDiarmid inequality just a simple application of Azuma Hoeffding's inequality. So this is also your homework. Okay.